Yeah, so we're just going to leave it. But thank you, because that is a little bothersome. But Ray, you said both spellings are correct?
Yeah.
Okay.
Are you sure about that?
I have no idea.
I mean the same thing. The only difference is that one's pronounced.
How do you pronounce that?
Well, one's homogeneous and the other one's not. But they should be the
I
same.
feel like for the hemp, the like homogeneous mixtures or something, it's just.
Yeah, I'm not, I really don't know. Okay, so do you guys remember how yesterday when we mapped from 2D to 3D, we simply took a 2D vector or point, if it were a position vector, and then had it just floating above the XY axis? Well, today we're going to talk about mapping between R3 and R4. So you can map XYZ to XYZ1, but you don't have to be stuck with this 1. You can make it H. So H can be any non-zero real quantity. And that is a homogeneous coordinate for XYZ. And if you do it correctly, then the ratio of x to h is x, y to h is y, and z to h is z. And so you can see that 1, 2, 5, 1 is homogeneous to 3, 5, 15, 3.
Wait. Homogeneous mixture, or sorry, matrix before meant like, that it was equal to 0, right?
A homogeneous matrix equation was where AX equals B was then AX equals 0. That was a homogeneous matrix equation.
These are homogeneous coordinates?
Coordinates, yep. Homogeneous kind of meaning same, which in my mind means proportional in this setting.
If anyone's interested, Ray and I have done some research.
Great.
And homogeneous with no second E was originally a biological term from homogeny, but today doesn't really have a use except in specific fields of biology that it refers to. So homogeneous is right, but people say between.
So I should be saying homogeneous.
I mean, it doesn't say anything about the pronunciations. It's just.
It's one of those things where it's
Like to differentiate the spelling.
Like.
Yeah, so like technically one is right, but in actuality.
How many E's should be in it?
2.
Okay.
Because like the homogeneous with no second E is where like it's like the whole like phylogeny thing from last year where it's like they have the same.
Ron, as an AP bio student, do you care to enlighten us?
How about homogenized milk?
That would be 2 E's.
Yeah, that would be 2 E's.
That would be 2 E's.
That's
Okay.
correct.
All right.
But it's
So
not really homogenized, right, everyone?
Right.
when we discuss
Yeah, I hedged my bets properly.
So did I.
I answered that and like, you hedged your bets, good job.
I mean, like, why would you ask that
I thought
question?
someone started
Because
something and I didn't.
truly homogeneous, right? What was he expecting? Like, yes, it's homogeneous.
Well, yeah, that is the case.
all right. In the large spectrum of those that have checked out and those that are trying not to check out, let's cater to those that are trying not to check out. We talk about 3x3 rotation matrices. Now, we have talked about rotating really within the 2-dimensional plane. But you can rotate within the 3-dimensional plane, and we've already done that when we talked about spherical coordinates, when we rotated kind of in front of the z-axis, or kind of pivoted about the z-axis. But we can rotate about the x-axis, the y-axis, or the z-axis. And the way I look at it is if you are rotating about the x-axis, that's Rx of theta, you then make the first row and first column I for I3. And then you place the rotation matrix in the other block. And then with Ry, so a rotation about the y-axis, you place I3 in the middle row, middle column, and then you place the rotation matrix with one kind of caveat.
What?
I think the only thing I can think of is that it has to do with the determinant, that the sign's location changes. But the cosine, in this case, sine, negative sine, cosine goes in the other missing spots to rotate about the y-axis. And then RZ, you replace the third column, third row with I3s, third column, third row, and then you have the block of the rotation matrix.
Is that because of like the minus j thing? The Ry, maybe? You know what I'm saying? Like
I do.
Okay.
That's the way I think of it,
Okay.
but I don't know exactly why. But it seems to have this kind of congruency there with that. So this is actually not in your textbook, so I wanted to give it to you here.
Do they expect us to like not do problems like that though?
I don't know why it was left off, because it's just such a part of like what you would do in terms of transformations. Is, you know, we're doing 3 dimensions. Why wouldn't you be rotating 3D? Okay. So let's talk about a rotation about the x-axis through 60 degrees. And we're doing a 4x4 matrix of the following transformation. So for this, since it's an x-axis rotation, in R1 column 1, we're going to have I3. So that's 1, 0, 0, 0, 0. That's like our I3 of row 1, column 1. And then we'll have cosine of 60. Negative sine.
Wait, cosine of 60 is...
Oh, sorry. I did sine. Negative sine. Sine. Cosine. And then you're going to fill in the 0. Oh, I'm sorry. 0, 1. There we go.
Why is it 4x4? Oh, yeah.
Because this is, again, a projection transformation. And then, just like we were able to transform a 2D vector by using a 3D matrix, we can transform a 3D vector by using a 4D matrix. So what we're going to use is I as a block, I3 is a block right here. There's I3. And then adjacent to I3, we'll have the translation vector. And then on the bottom, we'll have our projection into R4. So it's just so neat, we can translate. You just have to take it out of the plane it's in or out of the space it's in, and then you can just put it back in the space by eliminating that extra row and column. Questions, Alex?
Well, I'm going to confuse, why does it have to go in
Because you can't accomplish a translation without taking it out of its current vector space. Just like in order to translate any 2D vector you had to put H comma K in that third column. If you're translating a 3D vector, this is how you just add. Because if you were to come up with, let's say you want to translate vector A, B, C by this, okay? You'd have to write it as a homogeneous vector. So if I want to translate vector A, B, C, 2 to the right, 4 up, and -7 back, depending on how you want to orient your plane. I would then take ABC, put it into 4D, and then if I were to multiply this together, this would be, it's not?
It's not the right number of columns, right? No, maybe, never mind. No, that's me. I'm sorry.
Okay, so row by column. I think I did this right.
Yeah. Never mind.
Really keep shaking your head.
It's A plus 2, B plus 4, C minus 7, and then 1. So you've then translated your vector 2 to the right, 4 up, and then 7 back. But you couldn't have done that with another 3 by 3 vector.
Yeah.
Okay. Can I have a volunteer reader? Rohan.
A three-dimensional object is represented on a two-dimensional computer screen by projecting the object onto a viewing plane. We ignore other important steps such as selecting the portion of the viewing plane to display on the screen. For simplicity, let the XY plane represent the computer screen and imagine that the eye of the viewer is along the positive z-axis at point 0, 0, d. A perspective projection maps each point XYZ onto an image point X star, Y star, 0, so that the 2 points in the eye position below the center of projection are on a line.
Okay, so when people are designing animations, computer graphics, they have to think of where people are viewing, where the viewing screen is, and then where they are perceiving those objects to be in back of the screen. So a person would be at 0, 0, D, the screen would be at X, Y, Z, and then the perceived objects would be at X star or X star, Y star, 0. So we are going to watch a little video about perspective projections and how linear algebra is used to accomplish this in computer graphics. And I'm going to warn you, his voice is a little high, so just be good.
Okay.
We now come to perspective projection. If you look at objects around you, whether it's with your eyes, whether you look at computer graphics imagery, even if you look at art after the Renaissance, we see that objects that are further away become smaller. In fact, a common experiment is you place a quarter in front of your eye and you can block out the moon or the sun, when clearly they're much bigger than the quarter. Furthermore, if you look at something like railway tracks, you'll see that the lines, even though they're parallel, seem to converge in the distance, although they never actually do. This is perspective projection, where you have a center of projection, which is the camera of the eye location, and the geometry is as shown here. So this is your screen, and the line AB will project onto A prime, B prime. Of course, the further away it is, the smaller it will appear when projected. This is the standard projection model that is used everywhere, not just in computer graphics. and we're going to talk about the mathematics required to make that work. Consider this overhead view of our scene. This is the eye of the camera, so let me note that down. This is the eye. Here we have our screen or our image, and so we'll say this is the image. We have some location in the world, x, y, z, that projects to some location x prime, y prime, d. The question is, what are the coordinates at this point? So of course, the formulae for x prime and y prime are similar. We can just do one of them. The screen is assumed to be a distance d away, and the world space object is a distance z away. Now, the triangles are similar. So this triangle is similar to this whole triangle. And therefore, the length ratios should be similar. So I can say that d over x prime is equal to z over x. Let me just write that down. Of course, what I really want to solve for is what is x prime equal to. And so x prime I can bring here, and it will be equal to d times x by z. And so this implies that x prime will be equal to d times x divided by z. This division by z is really critical. That is what ensures that the object gets smaller the further away it is from the screen. And of course, we cannot divide by z using standard matrices, but that's where homogeneous coordinates really become useful, because to dehomogenize, you divide by the fourth coordinate, and one can create the matrix so as to put z in the fourth coordinate. So just bringing this up here, you can say, I just wrote it the other way and said d by x prime, but one can do it, write it in this form. You have x prime is equal to d times x by z, and y prime is equal to d times y by z. So what does the 4 by 4 matrix look like? X and y values do not change, but we are playing with the fourth coordinate here. So what I'm going to do is that I'm going to try to write this times some x, y, z, w to show you what happens. This will be equal to, so the x coordinate doesn't change, and so we can just write this as x. We can just write this as 1, and initially let's say w is equal to 1. Okay, so what happens to z? It doesn't change either. So the only change is in this fourth coordinate, where the w value I just multiplied by 0, so it's not even relevant, but what I'm doing is I'm taking minus z by d here. So minus z by d. Now if I dehomogenize this, you will see that x will be multiplied times d by z, y will be multiplied times d by z as we wanted, and in fact the z coordinate which I'm going to drop, if you also multiply by d by z, it will be equal to d, which is just a constant, which is where the image point is. Now, of course, the question is, why is the minus sign? Again, OpenGL convention, you're looking down the minus z-axis, and so the focal plane is at minus d. So again, I went through that verification already. You can do this formula, and it's x, y, z minus z by d. If you multiply it out, you get d times x by z times y by z minus d and 1. And in fact, this is exactly what you want to do in order to get perspective projection working. The next segment will deal with the derivation of GMU.
All right. So that is projective perspection. So the homework is just going to be to do a problem set review.
Yeah.